Good morning, everyone. Welcome to my talk. Today I want to talk about my work, which is about inventing malware detection system on graph structure. The name of my work is Manis. I'm Pen Su. I come from Technical University of Munich. Today, in our society, we can find many types of the mobile device. Of course, smartphones are not a basic life necessity. It means the smartphone is also the very important mobile device in our life. Android is the world dominating mobile operating system. It takes the biggest marketing share for the mobile operating system. Unfortunately, with the development of the Android device, Android applications, there are more and more attentions also attracted by the Android malwares, which says in 2017 we can find 2.5 million Android malwares. There is a study which says nearly every 8 seconds we can find a new Android malware applications, and also the nearly 10,000 per day we can find a new Android malicious. And also in the first half year of the 2019, we can find nearly 300,000 malware samples per month, which means 10,000 per day. Of course, this is a big topic, and also the attract many people, and also the many researchers, and also the many industry companies to do some work in this field. We can find the two big directions of how to detect Android malicious. The first one is the signature-based way. The other one is the machine learning-based way. Signature-based way is a very traditional way, and also is very common used in nowadays malware detection products, which use the signature to compare the malicious signature and also the benign signature. Machine learning based way is attract attention in recently, and also we can find some features of the malicious to classify from the benign samples. On the other hand, with the development of the machine learning, adversarial machine learning is also attract many attentions from research point and also industry, which focus on how to attack the machine learning system. From the technique point, we can divide the adversarial machine learning into the poisoning attack and also the evasion attack. Poisoning attack is mainly focused on the training step. Meanwhile, the evasion attack is focused on the testing step. We can also find some algorithms like the fast grading method and also the jockey map approach. Here there is an example. As a human being, I can find the both from both sides. The left side and the right side, both of them are pandas. But from the machine learning based classifying, it can see left side is a panda with the 57% confidence. But if we increase some adversary noisy, the classifying system will say this one is not a panda, this is a gimbal with 99% confidence. The other example is the stop symbol. Without any adversary noisy, we can say this is a stop symbol, of course, and we should stop before the stop line. But if we increase some adversary noisy, the stop symbol is not stop symbol here, it's become to a yard symbol. It means you don't need to stop before the stop line. The third example is MNIST. From the MNIST dataset, here we have the number 8, but if we inject some noise, the classifying system cannot find this, cannot detect this one is 8. It classed it. The number is 3. The last example is from the text processing. If we just change the sequence of the two letters in this sentence, we also can change the positive review to the negative review. It means very small change of the input can classify the sentence, the feature of the reviews. Okay, until now there are some questions I had asked myself. How about the machine learning? How about the machine learning based malware detection and the adversarial machine learning? How about the robustness? This is our first question. The other one is how can we craft this type of adversarial noisy? Okay, this is the reason why we have the money system here. First of all, I want to give a malware detection system, and then we will talk about the crafting way about this malware detection system. For the Android malware detection, we have manifest-based way, something like the permission-based way, and also the dangerous API-based way. On the other hand, we also have the struct information-based way. So we can use a control flow graph, data flow graph, function call graph, and program dependency graph to find the feature of the benign applications and the malicious applications. In our work, we use one function graph-based malware detection system. Here, we have a function, and each function is composed by. Here we have 5 steps, and we have 6 steps, and also the 5th step of the malware detection is the histogram extension and no histogram extension. Actually, from the original reference paper, we just have the histogram extension. And here we compared both of them. We found that the ROC feature with 2 situations and don't have the too big difference. And then with this situation, we give our mathematical model to craft adversarial noisy. Here, of course, we should have a detection system and use the loss function. We can find the gradients of the object function. Loss function, gradients, loss function, and then we can craft our adversarial noisy with some limitation. Here, the limitation is we cannot change the original graph in very big scale. It means we cannot change too much nodes on edge. The purpose of the adversarial noisy is maximal the loss function. Here we can say we get the loss function from loss and also from the label, from mass of the label and also the prediction. And the original graph is GI, and also the modified graph is the GR star, and we can get the GR star from the original graph, of course. In order to get the purpose of the adversarial noisy, we have 2 ways. The first method is the n-strongest node, and the other one is the gradient-based method. For the n-strongest node way, as a first step, we should find the node which has the largest influence in the graph, and then we inject those nodes, the n-strongest node, multiple times into the original graph in order to invent in the detection system. And for the gradient-based way, of course, we should calculate the gradient, and then we define a direction vector to find our modified graphs. Here for the unstructured method, we show the first step is initialization, which means that we should prepare the widget and find the unstructured node, which has the minimal right value. Here, why we use the minimal value? Because in our model, we define the malicious sample with the label 1 and also benign sample with the label -1. And our purpose to inject adversary noisy is change the malicious samples into the benign one, which will misleading the malware detection system. So we should find the biggest node, we should find the node which has the minimal value of the widget. And then after we find the unstructured node, we need to do our injection operation. The first step, we should present our unstructured node by the binary representation. And after that, we will inject the binary representation of the unstructured node into our neighborhood hashing step. And of course, feature embedding histogram step, and also no histogram extension and no histogram extension step. After all of them, we will get the modified embedding vector, and then put this vector into our classifier system until we will find our modified graph, which can mislead the classifier system. I mean, which can mislead the malicious application as a benign one. On the other hand, as the second method, I will talk about the gradient-based method. Here, for the gradient-based work, we also have 3 basic requirements. The first one is the occurrence of the graph's node cannot be expressed less than 0. Of course, the occurrence of the graph node in our situation is the number of the function which have the specific function embedding. And of course, the number cannot be less than 0. That could be 0 or more than 0. Yeah. And our second requirement is in histogram extension node, on 1 should align at the beginning of the p-dimensional vector. Of course, this requirement comes from the detection system. Requirement 3, we cannot reduce the original occurrence of the graph node. Of course, the occurrence number of the function called graph stands for the number of the function. If we can reduce the function from the graph, which means that we can remove one function from the original functionality, original application, which will break the functionality of the application. After talk about our requirement, I will show how to do our craft our adversary noisy. The first step, of course, that one is the gradient-based way. We should calculate the gradient. Yeah, here we have our detection system, and we have use our detection system and also object function, we can get the gradient. But here, unfortunately, for graph-based way, we cannot get the direct gradient directly, which can be used for the adversary noisy crafting, because our objective function is not continuous. Here we define another thing, which is the direction vector. Direction vector has the same direction with the grading. And then we will do grading vector adjusting, which can help our system to find the best way to craft the graph. Here, after calculating the grading, we can get the graph A, but each application cannot include all of the function, which means that we cannot find all of the elements of the gradient. So we, for example, from the graph A, which stands for all of the function, but in every application we cannot find all of the function, and then we should remove unrelated components from A to B. Here we remove two lines from A and get the graph figure B. From B, we have the one requirement which says we cannot include the negative element. So we should move line A to the right side by removing negative components. And then in order to keep the same direction with the graph A's red line, we should prolong the length of the line 2 in graph D and get the same direction line, the red line with the graph A. This is the basic idea of our holograms. The third step in our grading-based way is node projection. After grading computation and also the grading vector adjusting, we can get the vector like this one, but in order to meet the requirement in requirement 1 and the requirement 2, we should change our vector representation. In order to evaluate our work, we choose the dataset, binary set from the Andrew zoo, and we also use the various total to fit all of the binary samples. And for the malware samples, we get from the Debian dataset, which has the 5,560 samples. We divide our dataset into 5 folds. In our work, we also use the white box setting and also green box setting. White box setting, it means that it can access all of the information for the classifier, and also gray box setting, it means that we can only access limited information for the target classifier, but can get another classifier's information, which trained by another folds. Of course, in our work we have 5 folds. We also evaluate the histogram extension and the no histogram extension situation. Here, for the n-strongest node, we test 5 nodes and use the red box setting and the green box setting. Our result, we can get the 72% misclassification with red box setting. Just inject 22% nodes. We also get different misclassification rate with 2 and 3 strongest node injection. The last result is misclassification rate depends on the number of the strongest node, of course. For second experiment, we test with the histogram extension. Also use the 1 to 5 nodes. Result misclassification rate with histogram extension are lower than no histogram extension. Injection red box attacking get better misclassification than green box setting because we get more information. We also test our grading single best way. Here we use 2 parameters. The first one is the alpha, the other one is the threshold. Also use the red box setting and also green box setting. Here results Yeah. With histogram extension, here we see misclassification rate with histogram extension are lower than no histogram is, which is similar with the strongest node. And also misclassification with green books is lower than the red books. We also test with the random choice way, but with this we only get nearly 2% misclassification rate. Here we also show our result. Yeah. As a conclusion, we say in our work we talk about one malware detection system and also the adversary samples to invent this malware detection system with the strongest node way and also gradient sum-based way. Our limitation is we just evaluate the function called graph, and also we just test the graph kernel hashing embedding. We didn't test another stuff.